Alright, so let us consider interference from two sound sources. So let A and B be two speakers which are producing exactly the same sound. So that would mean that they're connected to the same sound system, same iPhone or same microphone or whatever. So they're producing exactly the same sound signal, or in other words, the signals produced by A and B are exactly in sync. And we have a microphone at location P. I'll just call it P. We have a microphone at location P. The question is, at the location of P, will we get constructive interference or destructive interference or something in between? That's what we want to find out. And we are also interested in what conditions would lead to constructive interference at P and what conditions would lead to destructive interference at P. Um, what would it mean to have constructive interference at P? You can see that in the diagram here, the upper one. At P, it turns out that the wave from A and the wave from B are exactly in phase, in sync. They happen to be exactly in phase. The distances are just right. And as a result of that, there will be the waves will reinforce each other, and that will cause the air to vibrate faster at P, and so there would be a large sound at P. I mean, that would cause the waves to the air to vibrate with a larger amplitude at P, and that would cause a loud sound at P. On the other hand, if you look at this second diagram, the wave from A and the wave from B are exactly out of sync. They're doing opposite things. So at the location of P, the waves will cancel each other out, and the air at the location at P will not vibrate at all. And so if you place a detector at P, a microphone, or even your ear at P, you will not detect a sound. So that is destructive interference. And constructive interference is when the waves reinforce each other and produce a large vibration or vibration of large amplitude at P. So we want to find out what are the conditions for constructive and destructive interference. All right, so we'll just recall one fact from chapter 15. So we had seen that when you have a wave, just a single wave, um, each point on the wave can be thought of as a simple harmonic oscillator, right? And we had discussed how each point on the wave is a simple harmonic oscillator, but it's also slightly out of sync or out of phase with its neighbor. So the second point that I drew is a little bit out of sync with the first one that I drew, and this one is even more out of sync. So in other words, the phase of these simple harmonic oscillators keeps changing as you go along the wave. And we had also discussed that if you consider a point A over here and a point B over here, which are separated by one wavelength, A and B are perfectly in sync, and so the change of phase between the simple harmonic oscillator at A and the one at B must be 2 pi because they're exactly in sync. So phase changes by an amount 2 pi if you go a distance lambda, because the distance between A and B is one wavelength. So how much does the phase change if you go a distance delta x? So by simple proportions, it's going to be 2 pi over lambda times, so what I meant to say is how much does the phase change delta phi if you go a distance delta x? And just by proportions, it's going to be 2 pi over lambda times delta x. This is just by proportions. All right, so in other words, if you travel a distance delta x along a wave, the phase will change by an amount delta phi, right? So let's keep that at the back of our minds, and let's consider a detector which is placed right here. So in the beginning, I mean, for our first example, let's just assume that the detector is placed equidistant between the points, from the points A and B. So let's place our detector P over here, and we are going to we are going to think about whether we are going to get a constructive or destructive interference at P. Now remember that the waves are completely in sync at A and B, right? So if you draw if you consider the wave coming from A and the wave coming from B, they have traveled exactly the same distance in order to get to P, because P has been placed equidistant from A and B. So if the waves have traveled the same distance, the delta x along this wave and the delta x along this wave is the same. And so the change in phase is the same, and so the waves will be perfectly in sync at P. So they were in sync when they started at locations A and B. They have traveled, we have traveled the same distance along each wave. So the delta phi, the change in phase, is going to be the same along each wave. And as a result of that, the waves will be perfectly in sync at P. So if P is equidistant from A and B, the waves will be in sync at P, right? All right. So that is so they, if they will be in sync at P, there will be constructive interference at P. All right. Let's look at another example. Suppose the point P is somewhere over here. We want to know whether we are going to have constructive or destructive interference at P. So the distance traveled by the wave from A in order to get to P is this distance, and the distance traveled by the wave from B in order to get to P is this distance. So now the waves are not traveling the same distance in order to get to P. So we don't know whether there is going to be constructive or destructive interference at P, but it's clear that it depends on the distances that the waves have traveled in order to get to P, because the distance traveled along a wave determines the change of phase that happens, right? All right, so there's a neat way of analyzing this. Let's consider a point S, maybe a point S on this longer distance here, such that AP is equal to SP. So we are choosing the point S such that AP is equal to SP. AP. All right. So the distance BS is going to be the difference in the paths. So BS is the difference in the paths, or the extra path traveled by the wave from B. All right. Now consider this. So let's call this is sometimes also called the path difference. And the symbol for it is delta L. So delta L is the path difference, or the extra path that one wave had to travel in order to get to the destination. All right. Now suppose delta L happens to be one wavelength. All right. So now let's think about now let's think what's going to happen. So A and B are completely in sync, right? What can you tell me about B and S? The wave at B and S, are they going to be completely in sync? The answer is yes, because we are considering a distance of one wavelength, right? So over one wavelength, the change of phase is 2 pi. So that means B and S are completely in sync. So we know that A and B are in sync. We know that B and S are in sync because of the path difference. because we have chosen delta L to be lambda. And so that implies that A and S are in sync, right? A and B are in sync, B and S are in sync, so A and S must be in sync. Okay, now if A and S are in sync, then what can you tell me about the waves at point P? So from S to P, the distance is the same as from A to P, and A and S are in sync, so you know that the waves will still be in sync when they get to P, because you can just think of S as the new source instead of B, and from S the waves are covering the same distance as they're covering from A, and so as a result of that you will get constructive interference at P. Constructive interference at P. Now, could you repeat the same logic if delta L was 2 lambda? Yes, if delta L was 2 lambda, then B and S would still be in sync, right? A and B are in sync, we know. So that means A and S would be in sync. And so from S to P and A to P, it's the same distance. So you know that the waves will be in sync at P. All right. So we can see the condition for constructive interference immediately. We can see that you get constructive interference at P if the path difference is m times lambda, where m is any integer, right? So that is the condition for constructive interference. I should have said n. So for constructive interference, the path difference has to be n wavelengths, where n is 0, 1, 2, 3. So it's an integer, any integer, okay. Now let's look at the condition for destructive interference, and you can probably do this yourself. So I'll just draw this again. I've got A and B, and I've got a point P which is not equidistant. So the distance from A to P is this distance, and the distance from B to P is this distance. And I am strategically choosing my point S such that it's the same. So S to P is the same as A to P, exactly what we did before. So SP is equal to AP. That's how I'm choosing the point S. All right, now let's consider, let's say that, so this distance B to S is delta L. Suppose delta L is equal to a half of a wavelength, right? So what can you tell me about the vibration at B versus the vibration at S? Are they going to be in sync or out of sync? The answer is S is out of sync with B. S and B are out of sync or out of phase. That means A and B are perfectly out of sync, right? So, sorry, I mean A and S are completely out of sync, not A and B. A and B are perfectly in sync. So if B and S are out of sync, that means A and S are also out of sync. So the waves are perfectly out of sync at A and S, right? Now they're traveling the same distance to get to P. So the change of the phase will be the same from that point on, and so they will remain out of phase, out of sync at P. So this implies that they will be out of sync at P, and so you're going to get destructive interference. Now the same logic would be true if delta L was 3 lambda over 2 or 5 lambda over 2 or 7 lambda over 2, right? It would be exactly the same logic. So you can immediately get the condition for destructive interference as destructive interference would happen at P if delta L was m times lambda over 2, where m is is an odd integer, 1, 3, 5, and so on. So m is 1, 3, 5, and so on. And that's it. So that's the condition for destructive interference. So whether you get constructive or destructive interference, um, depends on what the path difference is and how many wavelengths, how does the path difference relate to the wavelength of the wave. So if the path difference happens to be an integral number of wavelengths, then you get constructive interference, and if it's odd integral number of half wavelengths, you get destructive interference. So let's do a quick example problem. So on an open air, feel free to pause the video and see if you can work this out yourself. But the problem is saying that on an open air, at an open air concert, you are sitting at a distance of 7 meters and 9 meters from a pair of speakers. Um, a musician is playing a sound of 494 hertz frequency. And what do you hear in terms of intensity? So we again have two sources of sound, A and B, and your distance, you are the detector P. So your distance from A happens to be 7 meters from one source, and so 7 meters from one source and 9.1 meters from the other source. So what is the path difference? The path difference delta L will be 9.1 minus 7, which is 2.1 meters, right? Okay, so now you need to figure out the wavelength of the wave. So you just want to see which of these conditions is satisfied. Is it this one or is it this one? If neither of these are satisfied, then you know that it's something in between constructive or destructive interference. So in order to find that, in order to see which of these conditions are satisfied, you need to know what the wavelength of the wave is. So how would you find that? You can use V is equal to F lambda, and you're given the F. So you have to solve for the lambda. You're going to need the V, and you need the speed of sound. So there is this formula over here for the speed of sound in dry air, where you can just plug in 25 degrees centigrade to get the speed of sound. So once you get that, and I think I have it worked out over here, the speed of sound will be 346 meters per second. And then you can do V divided by F, and you will get the wavelength to be 0.7 meters. So this is going to be the wavelength. And then once you know the wavelength, you can see the answer right away. The wavelength is 0.7 meters, and the path difference is 2.1 meters. So that tells you that it's 3 times the wavelength. So we have this condition. Delta L is an integral multiple of the wavelength, and so there will be constructive interference.